Alright, so welcome to the video series on embedded systems. This chapter will deal with programming your first driver. So the purpose of this series is more or less to give viewers a high-level introduction to interfacing with peripherals such as sensors, actuators, and devices, communication devices. In this video, I'll be showing you how to program a driver for the SX1278, which is a LoRa transceiver. So you will be able to transmit and receive data over the air, and as far as I'm aware, you'll be able to communicate via the moon as well. That's right, there was a record recently set by a couple of grad students which managed to transmit a LoRa signal to the moon and receive it back. Alright, so hopefully you'll learn something. This video will just cover some just very basic to get you up and running with communications with this peripheral, the SX1278, and over the course of the series we'll see more in-depth usage of the embedded systems concepts. Alright, and well, what is a driver? A driver is a piece of software that lets us interface with a peripheral, be it a sensor, actuator, or in this case a communication sensor. These drivers usually run on a microcontroller. So in this case we'll be using the Raspberry Pi Pico, which has an RP2040 microcontroller on it. So it does not have an operating system, but you can run drivers on operating systems. And well, why should we care about programming drivers? Well, usually someone else has done us the favor of programming a driver and we can use it freely. Now, sometimes these drivers cover our use cases, and sometimes what I've sometimes had to do is maybe fix a couple things here and there in the driver, understand why I'm getting a certain error, and to do that I might need to edit the source code of the driver, and in some cases rewrite some drivers entirely because I've needed to vet them for use at a company, and maybe the error handling is not up to par to what is expected in the source code. So yeah, even if you're not planning on writing any drivers, this video may serve as a sort of demonstration of how someone would go about programming a driver. So the next up is, who is this SX1278? So I have a camera here. I'm going to start recording, and well, we have so when we talk about peripherals, these may come in various shapes and sizes. I have three different form factors of the SX1278. So this one comes with a little antenna you can solder on. So the module itself is quite small. I've done the job of soldering some pins to the pads, and let's see if you can sort of make out what it says. So this module right here is a 433 megahertz transceiver. This is the cute helicoidal antenna it's gone on. So this is what allows us to reach long distances by giving our signal more gain, both on the when we're transmitting and when receiving. And LoRa is a particularly well-suited protocol for long-distance transmissions, hence the name, long range LoRa. This is another form factor. It's got, I mean, you can tell the package is similar, though this one's got a socket for an antenna. Not sure if that's a micro SMA connector. Also labels all the pins. And yeah, it's also 433 megahertz. So yeah, I bought this one and realized I didn't have an antenna that could fit in there, and I couldn't get a hold of one, so I ended up asking for a friend if a friend lent me this one. I also bought this one just in case my friend didn't want to help me out there, but he came through after I had already received these, and luckily he did, because these are very small pads. This one's very hard to, I'd imagine it's very hard to get soldered, right? Because the pads are just so close together and tiny compared to these other pads, which are spaced out far apart in between. And well, let's see. Also labels all of its pins. And this one is also suited for 433 megahertz communications. Alright, so next up is datasheets. So when programming drivers, we often need to read and interpret datasheets. And even more so before the fact, we know which peripheral we're going to use, because datasheets are a source of information so that an engineer can make an informed decision on whether a peripheral is the right match for the application they're trying to solve, for the problem they're trying to solve. So maybe, so in the case of the SX1278, I've got the datasheet right here, and we can sort of look at the first page. First page gives us a very good description of what the system does and the very high level characteristics. So if I needed higher than 20 decibels for transmitting or receiving, I would need to find some other peripheral. So we read these datasheets to get a sense of whether the peripheral solves our problem, and then once it's in our hands, we can use it to program the driver for it. Well, I think then it's time to program the SX1278. So I'm going to go ahead and open up an empty folder and open up VS Code here. Let's close those up. And we will need, I will be using a couple extensions, like the Go extension, developed by the Go team at Google at the time of filming, and the TinyGo extension. I will have TinyGo and Go installed, and you can find, I'll leave a link in the description on how to get set up with TinyGo, compiling your first Blinky Hello World program. So first step to developing a driver with Go is to initialize the Go module. So Go mod init, we'll just initialized. This will give us IntelliSense, so it's just this just keeps track of our dependencies, which we will not be using. So, and we'll create a file, SX127x.go. And since this is going to be a package the user can import, we'll name it SX127x. And the convention in Go when writing a driver is to have the type which handles the operations, name it device, and this type will have the communications bus. So in this case we're using SPI. Now SPI is not a simple protocol by any means, but it is one of the simpler protocols. So I will go ahead and just show you how I go about abstracting away the SPI type using a Go interface. So this is the write buffer, this is the read buffer. So I've defined here, what I've done here is I've defined an interface which is composed of a single method in its method set called TX, stands for transaction. It takes in 2 byte buffers. The first one is the write buffer and the second one is the read buffer. So the only constraint here is that both have to be of the same length. So this is due to how SPI works. It's sort of let me grab the datasheet. So if we look at the datasheet, we have a page which explains sort of the how the device expects us to communicate via SPI. And what I just want to point out is this graph, which is a very common graph when working with electronic systems. It just shows us how the signals over the SPI bus, the cables, at what logic level they are. So when they're high, they're at the logic level high, which in this case would be 3 volts, since I'm using a Raspberry Pi Pico. And when it's low, that's 0 volts. So we can see that this NSS signal is starts out high and is low throughout the whole interaction, and then ends up at a high level again. But what I want to really focus on is the MOSI and MISO lines, which show us the data exchanged over the SPI bus. So what you'll notice is that, well, these squiggly lines mean that doesn't matter for the purposes of the communications. That signal can be at whatever logic level, and it will not affect the communications. And we see that there are 2 bytes exchanged. So we can see the first byte starts here with the WHR. I hope you can see my mouse. Yeah, you can see my mouse. The WHR bit, which is the write, not read. So that's a funny way they the naming scheme they've chose. Write not read bit, which means basically if it's set to 1, if that bit is high, then it's a write operation, and if it's at a 0, so the signal is at low, then it's a read operation. So the write not read bit followed by 7 bits representing the address, A6, A5, A4, all the way to A0. And after that, depending on this bit, we'll either write the byte we want to write to the register defined by the address, or we'll read from the address we passed in. So, and throughout this, what I want to sort of point to is these what the whole SPI interaction will happen as defined by these 4 bytes actually. Well, this the first read byte is ignored, so we don't really care about what it contains. But if we are reading an address, will be the SX1278 will store data, store bits here in the second byte of our read buffer. And if we are writing data, then the device will not store anything, or will store garbage basically we'll ignore whatever is written into here. But what we will be doing as the controller, the Raspberry Pi Pico, will be writing in this byte, the data we want to write into the address. Alright, I hope that was somewhat clear. These are the implementation details of how we go around. So what this says is pretty much what I've just explained here. So an address byte followed by a data byte is sent for write access, whereas an address byte sent and a read byte is received for the read access. Although this makes mention of only 2 bytes in both read and write access, the way SPI works is we'll need 2 buffers, both of 2 in length, so that we can capture that second byte or send that second byte, because SPI happens, so basically transmits both, uses both buffers simultaneously. So that's why it needs 2 buffers of same length. Alright, and something I didn't talk about, the NSS pin. This pin has to be connected to your SX1278 for the protocol to work, since it must be at a logic level of low throughout the whole transaction, and then can be then has to be pulled high, set high, to indicate that the transaction has ended, or else the device will not be able to tell whether the difference between two transactions, and it will confuse it. All right. So hopefully that sort of explains where I'm going here. And this is also like I haven't exactly pulled this out of thin air. This is a very common interface in Go. It's used in TinyGo, and the Perif library also uses this interface. So our driver we are writing right now will work for both TinyGo and Perif. So Perif is used for targets which have an operating system, like the Raspberry Pi 3 and Raspberry Pi 4, while TinyGo is more often than not used for lower level microcontrollers. So there we have our device, and what I'm going to go ahead and define is the new function, as is commonly done, which our user uses to declare the device. And this will return the pointer to device. Now, this would be illegal C. Maybe this has caught you off guard, but this is legal Go, because the compiler can tell that the device is actually being allocated, is pointed to the device being returned. So escape analysis tells the compiler it must heap allocate this memory. So this is completely fine in Go. And next step will be to I guess read a single register. And we are going to want to add an address, and we will receive a byte and an error. So and the way we're going to use the transmit, we need 2 buffers of length, both of length 2. So read buff is it's gonna be a new empty buffer of length 2, and write buffer we can straight ahead create it with our address and a 0 value. We don't, since we are reading the register, we don't need to write anything, so we just pass in a 0. And TX expects the write buffer first and the read buffer second. And once we're done, the read memory is going to be in the second byte of the read buffer. So return read buff, and there we go. Now you might have noticed we need to control the CS pin. So for TinyGo, that's usually done by having a machine.pin type in the device, machine.pin. But if in case I want to use this with the paraf library, which does not have the machine.pin type, I'm gonna even further abstract away this. So I'm gonna declare pin output, pin out, pin output, which is just gonna be a function which receives the level, which is a bool, either high or low. So there's our chip select, and we know that to activate the SPI line, you have to write false, right? We have to write a logic level of low. That's what we see here. And once we're done, we leave the line at a logic level of high. So I'm gonna go ahead and just create a method so that it is clear. CS enable CS. So CS enable. This will make it clear that we are enabling the SPI bus. So due to this inverted logic, since SPI expects CS to be low for the SPI bus to work, I found that maybe it's clear if I have a method that expects a more direct interpretation of the SPI line. So this could be SPI enable or activate SPI. CS enable is fine though. So call of true will set the CS line to low. Hope that's clear to everyone. And let's see. So I need the user to pass in a CS pin output. No. Well, so I guess what we're gonna try to do in this chapter is just check if the device is connected, if we are able to read from the device, and for that purpose, I'm gonna read from a register which has an expected value, a constant value. It's would be a read-only register. And in this case, reg version is a good candidate. At address hexadecimal 42, we expect to read hexadecimal 12. So I'm going to go ahead and define constants, reg version 0x42, and expected version. I'm going to go ahead and leave these unexported, 0x12, and gonna find my func device is connected. So I'm asking if the device is connected. Well, I'm gonna make use of my single register, so reg version. We can get the version and an error. And so if my version is equal to the expected version, I will return true because I've been able to read from the reg version register. And if not, let's just return false. And what's more, I'm going to go ahead and check the error. So and error is nil. So what I'm asking here is, hey, were you able to read the version correctly? Okay. If you were also able to read the version correctly, and there was no error while reading it, then I'm going to go ahead and say, yeah, we are connected and everything's okay. Now, you might want to ignore this error if you're, for some reason, you expect the communication to the SPI communication to sometimes throw an error, although the device is functioning correctly. But I'm gonna go ahead and check all errors throughout my series, or if not most errors. So this is already nearly ready for use. One thing I'm gonna want to do, because I've gone ahead and I've had some experience programming the SX1278, is I'm gonna want to reset. So this device does have a reset pin somewhere here. So the N reset pin, I'm gonna want to reset the device on before communicating it with it, just because if not, I'm not gonna be able to interact with it. So not sure where that comes from in this datasheet, but other drivers also do it. So I'm going to have a reset method, and I will have a reset pin, reset d.reset, and we're gonna write true to it. I'll explain soon. We want to hold that for 200 milliseconds, and so that's going to be our reset method. Sorry, I'm not documenting anything now. That'll come later. So what I'm doing here is I am guaranteeing that the cycle has a constant and fixed downtime. So whenever I reset my device, I guarantee that the reset pin is going to be down for at least 200 milliseconds and not more. That's why I'm writing a level of high before calling this method. It's a good practice for these deep resets, to ensure that they always have the same effect on the microcontroller. This initial part might not change anything, but I'm just going to go ahead and be a bit cautious. And and we're also going to need the user to pass in the reset pin. Reset. And with this, we should be able to already write our first program, which we'll be using TinyGo. Check connection. Check.go. So I've created a new directory, check connection, and I'm writing in files in here. Written a new check.go file, and I'm gonna bring in some pre-written code, just so I don't mess up. So my IntelliSense is not liking this right now, and that's because I have to select my target. Alright, this is not constant. It's a variable. And there we go. We've defined our constants, our pins, pin connection scheme. So clock is going to go to GP2. The TX pin on the Raspberry Pi Pico is going to go to GP3. RX to GP4, CS to GP5, and reset to GP16. And we're going to be using the SPI 0 interface. So first step is to configure the SPI. That's going to be SPI config frequency, and we're going to use 100,000. I'm just going to add an underscore in there so this reads better. This underscore has no functional effect on the code. It just makes it clear that this is 100 and this is 1,000, so it's easier to read, in my opinion. You can choose to write it as you wish. So SEK is going to be GP2. I'm just going to copy these in. SDO is TX. And SDI is RX. So I might have mentioned this before, but SDO is refers to MOSI, and SDI refers to MISO. Oh, it's in the comments. And serial clock pin. So I will check for errors on this, although pretty sure it's not going to error out. And what else? We are going to create our device 7X using our package. New, in case IntelliSense didn't pick up on the package, you can just import in SX1278X. Since you're inside the Go module, it'll pick up on you'll pick up that it's referring to this driver right here. So SPI, and let's use the CS pin here. Oh, and it expects the set method, right? This is a callback we're passing in. And the reset pin, set. We'll call it dev. And we'll reset it, and then we'll ask if it's connected. Else print ln. Alright, before compiling this, I'm gonna add a sleep in here, just so so I can pick it up in my monitor. I'm also gonna want to configure these pins, because if I don't configure them, they will not be able to write anything to the device. Output pin output. There we go. RST configure pin output. Alright, this could be before or after. So hopefully this will work. I'm gonna go ahead and turn on my camera and show you my setup right now. So this is what I've got set up right here. Hopefully you can hear me. Okay, let's move that microphone a bit. And well, I've already hooked up the corresponding pins of the Raspberry Pi Pico over to the SPI interface on my SX1278. And you'll notice I have two white cables that I've not made reference to throughout this video. That's because they are hooked up to the DIO and DIO 0 and DIO 2, which I will not be using. So you can just take those for what they are, useless cables. The yellow cable is used, that's GP16, that's the reset cable, so very important to have that there. And well, here we go. One thing you might want is to power your SX1278 with an external power supply. I'm using this Unity supply at 3 volts. You can see it's on right now, but it's consuming 0 amps. That's because it's this device, the SX1278, is very power efficient. Alright, so back here, let's go ahead and flash our program to the Pi Pico. Our target is going to be the Pico. We're going to want to monitor the output so we can read what the Pico prints back. And we're going to compile our check connection program. And I'm going to turn off my camera there. So once it finishes and compiles, it will look for the Raspberry Pi Pico over USB, and hey, oh, there it worked. I had to power cycle the SX1278. So, alright, so that pretty much concludes this chapter. I hope this sort of helped explain some of the concepts used in embedded systems programming. That's the code for that runs on the Raspberry Pi Pico, and well, this also runs on the Raspberry Pi Pico. This is the driver for the. So I won't be uploading this because, well, it's too small, but I will provide a link to the final result of this driver. So that's all I got for you. See ya in the next one.